Welcome to this explainer. All right, let's jump straight into a seriously fascinating cosmic investigation today. We're looking at a recent exoplanet discovery that literally shattered our best scientific models. We're going to unpack exactly how astronomers managed to spot a hidden world and why its atmosphere is forcing us to rethink, well, pretty much everything we thought we knew about giant planets. So what actually happens when a cosmic discovery breaks our best computer models? That's really the core of our detective story here. For decades, astronomers have been building these incredibly complex simulations to predict what distant, mature planets should look like. But then, what happens when the actual data from a freezing, newly discovered world totally contradicts those simulations? Well, it forces our brightest minds to completely rewrite the rulebooks on planetary atmospheres. Section 1. A cold, distant giant. Let's meet our prime suspect. This planet is located just 12 light-years away from us in the southern constellation Indus. Now, 12 light-years might sound like a lot, but in the grand scale of the universe, it's practically right next door. It's actually one of our absolute closest planetary neighbors. And the sheer scale of this thing is just staggering. It is absolutely massive, weighing in at 7.6 times the mass of our own Jupiter, even though its actual physical diameter is roughly the same. Just imagine cramming almost 8 Jupiters into the space of one. That's the incredible, mind-bending density of the super Jupiter for you.
Temperature here is chilling. Literally. We're talking about a range somewhere between -70 and +20 degrees Celsius. While that might sound absolutely freezing to us down here on Earth, it's actually slightly warmer than our own Jupiter. Why is that? Well, because Epsilon Indi AB is actually still radiating residual heat from its violent formation billions of years ago. And over the next few billion years, it's just going to continue to slowly cool down out there in the dark.
Section 2. Seeing the invisible. You see, finding a dark, freezing planet like this was previously deemed almost impossible. But astronomers actually pulled it off using a technique called direct imaging paired up with a device called a coronagraph. Think of a coronagraph kind of like holding up your hand to block the bright sun so you can see a bird flying right next to it. By blocking out the intense, blinding glare of the host star, the faint thermal glow of the exoplanet itself is finally revealed to us. So the crucial takeaway here is how we found this one compared to how we usually find planets. For years, scientists really suspected this planet was out there because of indirect detection. Basically, they measured this tiny back-and-forth gravitational wobble in the host star. But since this planet takes roughly 200 years to complete just one orbit, that wobble data was super incomplete, and predictions about exactly where it was were way off. Direct detection totally changed the game. Instead of just guessing the planet is there because the star's wobbling, astronomers captured its actual, incredibly faint infrared light. And that brings us to our absolute hero tool for this job, the NASA James Webb Space Telescope. Because this planet is so incredibly cold, most of its light is emitted in the thermal mid-infrared spectrum. Webb's mid-infrared instrument, or MIRI, is just perfectly suited to see these cold, faint objects. It gave astronomers the unprecedented thermal vision they desperately needed to actually spot Epsilon Indi b. Section 3. The missing ammonia mystery. Okay, so when the JWST data finally came back, scientists hit a massive anomaly. Based on all the standard theoretical models for a planet of this exact temperature and age, astronomers had very, very specific expectations. They predicted an atmosphere with a solar metallicity composition rich in methane and carbon. But most importantly, they expected it to be totally packed with ammonia gas and completely devoid of clouds. Basically, a clear, highly toxic sky. To actually measure that ammonia, astronomers compared the light coming from the planet at 2 different wavelengths, 10.6 and 11.3 micrometers. Now, ammonia gas absorbs light heavily at 10.6 micrometers. So obviously they expected to see a huge drop in brightness at that specific wavelength. But when the data arrived, wow, the signature of ammonia was shockingly shallow. It just wasn't there in the massive amounts predicted by the computer models. Which presents our ultimate cosmic mystery, right? Where did the ammonia go? If Epsilon Indi AB has the perfect temperature and conditions to harbor vast amounts of ammonia gas, what on Earth, or well, what on this exoplanet, is hiding it? Did the planet somehow form with less nitrogen, or was something physically blocking our view? To crack this case, the team actually went back and looked at the archival data from ground-based telescopes. This data showed the planet was unusually faint at shorter near-infrared wavelengths, right between 3 and 5 micrometers. And this missing near-infrared flux? That was the final, vital clue for our astronomical detectives. Something was actively blanketing this planet. Section 4. A cloudy solution. So, the culprit behind all of these missing signatures? Clouds. But we're not just talking about any clouds. Thick, patchy, water ice clouds. These clouds act exactly like a massive thermal blanket. They muffle the near-infrared light from escaping the planet, which makes it look incredibly faint to our ground-based telescopes. And crucially, they form a thick layer high up in the atmosphere, physically hiding those deep reservoirs of ammonia gas that are trapped underneath them. Just try to imagine Earth's high-altitude cirrus clouds for a second. You know, those thin, wispy clouds you see way up high on a cold winter day? Now imagine those on a massive, global scale, wrapping entirely around a freezing gas giant. That is exactly what we are looking at on Epsilon Indi A. And, okay, here is a surprising, maybe slightly gross fact about this planetary chemistry. Because ammonia and water are the primary components of urine, visiting this cloudy, freezing planet would come with a distinctly pungent smell. It's a fascinating, if maybe a little unappealing detail about the harsh realities of atmospheric chemistry on these giant worlds.
Section 5. Rewriting the rulebook.
This discovery absolutely changes everything we thought we knew. As researcher James Meng points out perfectly, it's a great problem to have. You see, previous atmospheric models largely just ignored clouds because calculating the physics of cloud formation makes the computer math incredibly, ridiculously complex. It was just easier to assume clear skies. But this discovery, it proves we just can't do that anymore. It forces theorists to finally update their simulations to include the chaotic reality of actual planetary weather. Because Epsilon Indi AB is so incredibly well studied now, its mass and its thermal glow are highly mapped out. By confirming that mature cold giants can indeed have complex water ice cloud coverage, this specific exoplanet serves as a vital benchmark. Pretty much every future astronomical model trying to understand the evolution of gas giants is going to be calibrated against this exact world. So let's quickly summarize the massive impact this has on astronomy. First off, it definitively proves that the James Webb Space Telescope can directly image mature, cold planets, not just the really hot, young, glowing ones. Second, like we talked about, it completely revolutionizes atmospheric modeling by forcing cloud physics into the equation. And third, understanding the chemistry and weather of this cloudy superJupiter is just an absolutely essential stepping stone if we ever want to eventually characterize the atmospheres of small, habitable Earth-like worlds. We've got to perfect our techniques on these giant neighbors first. Let me leave you with this final thought. If our closest superJupiter, literally right in our cosmic backyard, was hiding such a massive secret beneath its clouds, effectively breaking our best scientific models, what other breathtaking mysteries are waiting for us out there in the dark? We are truly just scratching the surface of what the James Webb Space Telescope can reveal. Thank you so much for joining me on this explainer. Keep your curiosity sharp, and I'll catch you next time.